Well, hello, ladies and gentlemen. It is 6:45 and it's time to get started. Welcome to those who are online as well to our 2021-2022 Senior Design Electric Baja presentation. My name is Esden Yeager and I am the mechanical engineering lead on the project, and we were led by Dr. James Brooks, who was our academic advisor. As many of us know, the electric vehicle market is rapidly growing and becoming more popular with car manufacturers such as Tesla, Rivian, Ford, various others who are trying to reduce their fossil fuel emissions. E Baja is a collegiate design series that is designed for single-seater off-road vehicles. And for this project, we used the platform of one of our old cars that is retired due to its age for this project. SAE E Baja competitions do not exist. However, this is a prototypical design to show other colleges and SAE as an organization what E Baja might look like in the future. This car that we built was designed to match or exceed the current performance of the gas alternatives, and its purpose for Grove City was to show that as an engineering department, they are a leader of innovation as well as hopes to bring positive attention to the campus. So Baja cars tackle various rough terrain and off-road obstacles such as rock crawls, high-speed driving over large obstacles on the track, such as telephone poles that are laid over and various other large objects. And they are also run on motocross tracks, and they also have to deal with high jumps on motocross tracks. The other thing that they have to do is various technical dynamic events that test your steering and your maneuverability and various more technical parts of the car.
Hello, my name is Bryson Gray. Some of the general requirements for this project is we wanted to maintain a maximum of 12 horsepower in our electric motors. The desired top speed for this design would just be 35 miles per hour, and the car should be able to drive for at least 45 minutes at a race pace. Additionally, the car should implement regenerative braking to assist in battery life and recycle that power that is otherwise wasted. The car must display the remaining battery life and speed to the driver by means of the monitor display at the front of the vehicle. And additionally, we want to stay close to our $8,000 project budget. Some of the safety requirements for this project is that the car must be equipped with a shutdown circuit. In this shutdown circuit, there are 2 e-stops, an inertia switch, as well as a battery disconnect. Rotating parts of the drivetrain must be enclosed so that fingers and feet and any other parts of your bodies cannot be seized into the mechanisms of the car. Additionally, a firewall must be implemented that is suitable to protect the driver from both fire hazards and electrical hazards in the case of any incident.
So, my name is Sean Cook, and I was mainly responsible for working on the drivetrain. So, the first step in making an electric car is selecting your electric motor. This is the motor we decided to go with. It is the 2021 40-volt Torquey motor. This motor was recommended to us by our partners at Golf Carts Unlimited. We have 2 of them. That way we can control each wheel independently of each other. Combined, the 2 motors have about 12 horsepower, which is just 2 more horsepower than we had before with our gas engine. One motor itself can put out about 80 foot-pounds of torque. After our gear reduction, that leads to about 240 foot-pounds of torque per wheel in the rear. And the motor has a maximum RPM of just under 1,800, and that will give us a max speed of 42 miles per hour without any losses. So moving on to the overall architecture of the drivetrain, we have 2 mirrored assemblies. That way we can completely control each wheel independently. So we start off with the motor, and then we go to the gearbox. The gearbox, its sole responsibility is to change the direction from a vertical rotation to a horizontal rotation. That way we can actually use it in the wheels. From there, it goes to the sprocket and chain, and this is where we actually achieve our 3-to-1 gear reduction. Moving on from there, we go to the final drive, which hooks up to our CV axles and later on into our wheels. So the first major component of the drivetrain is the mighty gearbox. Just to explain a little bit, the purple on the screen is the nuts. This allows us to torque everything down and keep everything nice and solid, and allows us to pre-tension the tapered roller bearings. The tapered roller bearings are actually highlighted in blue. There's 4 of them, and these are used to handle the thrust loads of the gears, because the gears, when you put load on them, actually want to push each other apart. So we need those to keep that from happening. The red are spacers, or the red are backstops to press the tapered roller bearings against. The green are spacers, and then the yellow are just the shafts. We also ran rigorous FEA on this. FEA is just finite element analysis, and this is a way of determining where our high stresses are, and that way we can better adapt our design to where those high stresses are.
My name is Hunter Hughes, and I worked with Sean in the subsection that we deemed the drivetrain. What we can see here in front of us is the final drive of the vehicle. The final drive is made up of 3 components: a sprocket, a final drive core, and a bearing block. With this sprocket design, we are able to achieve a 3-to-1 reduction of the motor. This drops our speed to 1/3 of the motor speed, but increases our torque to 3 times the motor torque. This was accomplished using an ANSI 40 roller chain sprockets, a 45-tooth sprocket on the final drive, and a 15-tooth sprocket on the motor to be our 3-to-1 ratio. The ANSI 40 chain that was selected is a hardened chain that has a 960-pound working load. This 960-pound working load is the maximum load in tension that the chain can withstand on a cyclical means, such as in use. With our design, we're only actually rated at 640 pounds, or producing 640 pounds of tension in our drivetrain, meaning we are well below the working load, thus ensuring the durability of the chain. The main purpose of this assembly before you is to convert this sprocket drive from the original motor into a spline drive for our CV axles. The Baja car has always had CV axles, which have been very proven, very tested by our previous designs, and we wanted to maintain as much of the original design as possible. Finally, you can see that there are built-in tensioners in these blocks. The long screw coming off of the back actually protrudes through the car, allowing for the chains to be precisely tensioned in order for them to function properly. Right here, this is what I call the final drive core. The final drive core, as you can see, is made up of 3 main components. You have a large flange, as seen by the left, with a total of 8 grade 8 bolts in it. This is what we use to actually attach the sprocket to this splined drive shaft, allowing for the adaptability of other size sprockets in case we choose to change the gear ratio, along with a very strong and robust design. There is a custom part with the Honda inboard CV spline made into it, so that way the traditional axles that we already have in stock can be used with our sprocket design. And finally, it's balanced between two sealed roller bearings. These provide adequate surface for the drive to spin freely, along with providing enough torque and leverage against the design so nothing walks out of place. The main benefit of this overall design is that it allowed us to use the existing geometry of the car, including suspension, tube members, and axles. As we can see here, this is a good picture of our drivetrain to the left. In the blue box, we have the 2 yellow motors. Those are our full-size motors. Below them, a little bit difficult to see, but right here is our miter gearboxes, the ones that Sean was talking about. Those are then followed by a sprocket to chain design, which shows the rear drive right here. The rear drive would then have a CV axle protruding out. The CV axle can actually be seen in motion in that video that just recently played for us, showing everything in motion. One of the few changes we did have to make to the suspension was the addition of dual shocks, the purpose of which the car got a lot heavier in the back, so we needed to have a bit more lift force. Moving on.
Hello again. Some of the necessary frame adjustments for this project included creating a front braced car. So here's a picture of the original rear braced frame, and in the middle is the new front braced frame. The only modification from that is the vertical tubing in the front, which allows us the flexibility of altering the rear of the frame chassis. This frame was redesigned from the existing gasoline-powered components to our new electric-powered components, which were drastically different and needed a complete redesign. As you can see in the very far right-hand picture, there's a close-up of the rear frame. It shows the detail and the intricacies of the framing network so that we could get all of our components to fit inside the outer roll cage of the chassis and interact with each other. All of these frame modifications were compliant with the E Baja rules. Additionally, an FEA was ran on the frame chassis. For this particular FEA, we simulated a 5G drop, which is comparable to what a car would experience if it goes off a large jump. The results of this were a max stress of 29.8 KSI, which results in a factor of safety of 2.2, which leads us to believe that this frame is very sufficient going off of any jumps that we throw in its way.
My name is Trevor Stevenson. I'm one of the electrical engineers on the project. Powering the car is a battery system made up of 4 12-volt batteries wired in series to give a total output of 48 volts. We use lithium-ion batteries. They are much lighter and much cleaner than lead-acid batteries. Specifically, we used lithium iron phosphate. We made a decision based between 6 lithium-ion batteries based on energy output, weight, price, safety, availability, supply chains. We had to deal with all the supply chain issues that everybody else has in the past 2 years. And we came to the conclusion of lithium iron phosphate. These batteries have a 900 amp peak current, which is the current supplied when you initially turn on the motors. So it actually jump starts the motors and gets off the line. The energy rating is 70 amp hours. What that means is that it can output 70 amps continuously for a grand total of 1 hour. And this gives it an approximate runtime of about 45 minutes as the continuous current is closer to about 100 amps. Oops. The controllers we used Alltrack's XCT 48500 motor controllers. Decision to use those was helped in great deal by our friends at Golf Carts Unlimited, who have been absolutely fantastic throughout the entire course of this project. They are golf cart controllers, so they work perfectly with the motors that we used, and they, in their main role, help cut off all power if voltage gets too low, so the batteries get too far drained, or they start to overheat, just for safety measures. There's also a lot of reprogrammable features, including max voltage, max motor speed, reverse speed, armature current, even driving mode. It offers a lot of controllability, and it comes with a very helpful monitoring software that shows gauges of actually what kind of voltage is being supplied from the batteries to the motors, and helps us to make some of our decisions for controls.
All right. Hello, I'm Corey Turbio, electrical engineer. So here is a simplified version of the power diagram. On the far left, you have the lithium batteries, which Trevor just talked about. And right after that, you have the big disconnect. It's actually from like a boat, and it's for turning it off when you're moving the car or storing it. After that, you have a lockout, which is like a key which people are used to, and that gives power to everything. So first, on the top of this, the lockout gives power to the 2 buck converters. These just step the voltage down from 48 volts DC to 12 and 5. This powers all of our smaller electronics and microcontrollers. Additionally, out of the lockout, it goes to an inertia switch and the E-stops. So these cut off power if anything anyone wants to, or if you hit anything, such as a tree. Below that, you have the tow run switch that arms the car to be in run. Basically, if it's in tow, you can push it, and if it's in run, it will try to regenerate, so you don't want to push it. And then after that switch, it closes both the contact relays, which allows power to pass through to the golf cart motors, to each motor. Here is the communication diagram. This is roughly how everything's talking to each other on a high level. On the far left, you have sensors. This is input and feedback. If anyone saw in the car, we have an encoder above the steering wheel, which tells you the steering wheel position. We also have a potentiometer in the foot switch as well. So I'm sorry, I meant a potentiometer on the steering wheel and one in the foot thing. There is encoders as well on the motors. And all this data goes into the MyRio, which is our main controller. And this sends output commands to both the motor controllers, which go to the motor, and also hosts a server where a Raspberry Pi can look into the controller and find data to display to our monitor. Here's roughly how things were implemented on our car. With the Raspberry Pi, we made a client to request data from the server and a graphical user interface. And these two elements were combined to have a display in the front of the car. And for integration of the master controller, you have a fuzzy controller, which is our control scheme, which Trevor will talk about soon. We have an encoder, which just gives us the wheel speed, and the server, which talks to Raspberry Pi, and those are all integrated. The network, here's roughly what it looks like. The Raspberry Pi sends these 3 pieces of information. It just says, hi, I'm the Raspberry Pi, here's the time and here's the date. And the server returns all of this information. Most importantly, it tells us the miles per hour, the miles driven, which is displayed.
My name is Zach Spries, and I'm one of the mechanical engineers on this project. In order for the driver to receive feedback from the vehicle, as well as to communicate with the controls, we use the system outlined on the screen. As Corey mentioned, we took a potentiometer and integrated it into the throttle pedal, so that way the driver can take their physical motion of the pedal, and it will be converted into a digital signal that can be read by the controllers. We did the same thing for the steering potentiometer. In order to use the torque differentiation of our system, we need to be able to track the steering wheel's angle. We did that using the potentiometer mounted on the column with a belt reduction system to stay within range of the potentiometer travel. We also have switches mounted on the dashboard, so that way the driver can select which driving mode they wish to be in, whether they switch to run tow mode, or selecting that the car is ready to be armed and they're ready to drive. We used motor encoders on the engine of the motors in order to calculate our gearbox speed. Since we don't have any other sensors on any of the wheels, we were able to calculate the motor rotation from the motor encoders and output it onto the screen and calculate what a theoretical speed is. We also have a sensor integrated into the brake pedal, so that way we can tell whether the brake is being actuated. This is another safety measure, so that way we don't have both the brake and the throttle being run at the same time, leading to deterioration of the drivetrain. The user can be able to tell what the speed is of the car and what else is going on via the monitor outlined in the blue box on the car. This is a 15-inch computer monitor with a 1000 nit brightness, enabling it to be seen during the day. This is within view of the driver, even when they're in full race gear, and does not impede their vision whenever they're driving. As mentioned before, we have a key lockout mounted on the dashboard as another safety feature to keep the car from being activated by anyone who is not qualified to drive. We have a driver ready button mounted on the dashboard to arm the car once the driver is ready to go. They press this button, thus enabling the tractive system, and the car is ready to drive. We have a crash inertia switch mounted on the underside of the steering wheel, so that way in the event of a crash, the tractive system is disabled, therefore protecting the driver as well as our drivetrain. We have 2 e-stop switches on the vehicle. One is on the outside, so any spectators can disable the vehicle in an emergency, and one on the inside of the vehicle within reach of the driver, so that way they can deactivate the car in the event of an emergency. We have 4 lamps located on the car in the very, very front, so that way the driver can view which drive mode the car is in and whether it's able to be towed or in run. As mentioned before, we have the forward, reverse, and tow run switches within reach of the driver. On the left-hand side, this box showcases our dashboard with easily read labels. All these are color-coded with the ones for their corresponding lights on the right-hand side. The very bottom features our key switch, then we have our run tow switch, forward, reverse, and finally our driver ready button at the top. The left-hand picture shows our crash inertia switch located on the underside of the steering column within reach of the driver even whenever they're in full race gear. On the right-hand side, in the blue box, showcases our cockpit e-stop button, which is, again, within reach of the driver near their right hip. So in the event of emergency, they can easily let go of the steering wheel and smash the e-stop button, disabling the vehicle.
Hello, my name is Morgan Prudinski, and I'm an electrical engineer working on this project. Here on the screen, you can see this is the display that the driver would see while driving. So it's showing the speed of the vehicle in miles per hour, along with the drive time that they've been in the car since it's been powered, and then also the distance driven, and that's also in miles. The other important indicator on the screen that the driver can see is the battery level. So this is obviously very important because then the driver has some indication of how much longer they can drive before they need to charge their batteries again. And all of the actual data for this is coming from the MyRio and is sent to the Raspberry Pi over the server that Corey talked about earlier. And the Raspberry Pi is what is actually sending data to the screen over an HDMI to display it here. So I'm going to talk a little bit about how we controlled the two rear independent motors that we had on the vehicle. So we don't have a physical differential on the vehicle, so we wanted some way to do sort of a virtual differential. We were able to accomplish this by using a control strategy called fuzzy control. This controller uses both the throttle input as well as the steering angle to calculate a differential value that will be either added or subtracted to the right and left motors, depending on the direction of your turn. So for example, if you're making a left turn, the right motor would get more power than the left, and that would help push the car around the turn, and that will help reduce understeer, which is essentially when you're trying to make a turn and your car is going a lot more straight than you'd like it to. In this video, it's showing a simulation of how the fuzzy controller actually works. The graph on the right shows all the inputs and outputs that are possible in the system, and those red perpendicular lines that you see are actually the exact output that you're getting from the given inputs that are on the left side of the screen. So one of the examples that's shown in this video is as the steering input changes, the differential will change as well. One of the main ways that it's used is as the steering angle is more dramatic for a hard right turn or a hard left turn, that will change the differential, as well as the throttle input being increased. We did create something what we call a deadband, which is essentially if somebody's pressing the throttle at full throttle, or if they're trying to drive straight, both motors will receive the exact same power so that either you can go as fast as you need to or drive in a straight line without the wheels trying to assist you on a turn.
Hi, my name is Trevor Iltis, and I'm going to be talking about the testing and vehicle performance. So the first phase of our testing involved this test stand that's shown in the video here. So the main purpose of this was to kind of gain familiarity with the hardware that we had for our drivetrain, and it also allowed us to get our motors spinning prior to having the actual frame of the car constructed. So our test stand was comprised of one of our motors, one of our electronic speed controllers for the motors, one of the Ultrax controllers, and the four 12-volt batteries that comprised our battery pack. As I said, this allowed us to spin up our drivetrain prior to having all components finished, and it also allowed us to do some initial testing with our fuzzy controller. The second phase of our testing took place on jack stands. So basically, this came after the vehicle had been mostly completed and all parts had been put in the vehicle. So we elevated the rear of the vehicle, which is where the power is being delivered, so that the car can be tested without it moving. And this allowed us to test kind of the complete end-to-end system of the vehicle, along with the peripherals like the monitor and the switches and the lamps that Zach and Corey were talking about. This setup also allowed us to test things like our torque vectoring, which is shown in the video here. If you watch, as that potentiometer in the front is changed, the wheel speed changes to the left and the right, depending on which way it's being turned. Additionally, we were able to test a lot of our safety features like the inertia switch and the e-stops, and we were able to test our regenerative braking system, which, as was pointed out earlier, allows power to be fed back into the batteries during deceleration. The third and final phase of our testing was obviously having the car on the ground and driving it around. So this is basically the car was fully wired and had been fully tested to a satisfactory safety level on the jack stands. It allowed us to test the drivetrain fully loaded, so the car had a driver in it, so the weight of the driver along with the friction and the power necessary to move the whole vehicle. In this phase, we were able to do some tuning to our throttle response. Initially, the pedal had quite a bit of travel before the motors were kicked in, so we were able to tune that out through software. We were also able to test our braking performance, which is shown at the end of the video, which just restarted. But we were able to lock up all four wheels, which is a Baja safety requirement. Additionally, we were able to assess some other driving dynamics like the turning radius. So today we actually ran a test where we were able to check the radius of the car, and it had a turning radius of 57 inches, which is just under 5 feet. In contrast to the original gasoline power car without torque vectoring, the turning radius was 7 feet, so it was almost a 2-foot improvement to the turning radius. Additionally, we were able to test the top speed of the vehicle, and we were able to assess that the vehicle has a current top speed of 38 miles per hour. We did unfortunately run out of track. It might have been able to go a little faster, but that's still it exceeds our initial design requirements, and it exceeds the speed of the original car, which was 36 miles per hour. We're all very excited about the future of Electric Baja and the implications of the success of this project for potential competitions. And we'd all like to thank you for all your time and attention. And now we would be happy to field any possible questions that you guys might have about the project.